Welcome to Fast Learn Academy and Easy Scholar. Today, we're diving into the fascinating world of computer science and data structures. Whether you're a beginner or looking to deepen your understanding, this lesson will give you the tools and knowledge you need to excel. Don't forget to like, share, comment and subscribe, and hit the notification bell to stay updated with more exciting lessons from Fast Learn Academy and Easy Scholar. Let's get started.
Introduction to Computer Science Overview. Computer science is the systematic study of algorithms, data structures, software and hardware, and their applications. It encompasses theoretical studies of algorithms and computational systems as well as practical applications of those studies. Core areas of computer science algorithms and data structures. Algorithms are step-by-step procedures or formulas for solving a problem. Data structures are ways of organizing and storing data so that they can be accessed and modified efficiently. Importance: algorithms and data structures are fundamental to efficient programming and problem-solving in computer science. Programming languages: low-level languages, close to machine code, example assembly. High-level languages, more abstract and closer to human language, example Python, Java, C++. Importance: understanding different programming languages helps in selecting the right tool for a particular problem. Software engineering involves the systematic development and application of techniques and principles to create high-quality software. Key concepts include software development lifecycle, SDLC, version control, testing, and maintenance. Operating systems and operating system, OS, manages computer hardware and software resources and provides common services for computer programs. Examples: Windows, Linux, Mac OS. Importance: understanding OS concepts is crucial for optimizing and troubleshooting system performance. Computer networks: study of interconnected computers and devices that share data and resources. Key topics include network protocols, example TCP, IP, network topologies, and network security. Importance: networking is essential for communication between computers, the internet, and cloud computing. Databases: systems for storing, retrieving, and managing data. Types: relational databases, SQL, and NoSQL databases. Importance: databases are vital for managing large volumes of data and applications. Artificial intelligence, AI, and machine learning, ML. AI involves creating systems that can perform tasks that usually require human intelligence. ML is a subset of AI focused on building systems that learn from and make decisions based on data. Importance: AI and ML are transforming industries with applications in automation, predictive analytics, and more. Cybersecurity: practice of protecting systems, networks, and programs from digital attacks. Key concepts include encryption, firewalls, and security protocols. Importance: as digital data becomes more valuable, safeguarding it from threats is paramount. Human-computer interaction, HCI, study of how people interact with computers and designing user-friendly interfaces. Importance: good HCI can improve user satisfaction and efficiency. Fundamental concepts: computational thinking, problem-solving process that involves breaking down problems, recognizing patterns, abstracting general principles, and developing algorithms. Binary and data representation: computers use binary, zeros and ones, to represent and process data. Concepts include bits, bytes, and encoding schemes. Example ASCII, Unicode. Mathematical foundations: mathematics is fundamental in computer science, underpinning areas like algorithms, cryptography, and computational theory. Key areas include discrete mathematics, calculus, linear algebra, and probability. Theory of computation studies the capabilities and limitations of computing machines. Key concepts include Turing machines, decidability, and complexity classes. Example P, polynomial time, versus NP, non-deterministic polynomial time. Software development methodologies: structured approaches to software development. Examples: Agile, Waterfall, DevOps. Importance: Methodologies help in managing and executing software projects effectively. Practical applications: web development, creating websites and web applications. Technologies: HTML, CSS, JavaScript, and frameworks like React, Angular. Mobile app development, developing applications for mobile devices. Platforms: Android, Java, Kotlin, iOS, Swift. Game development, creating video games. Tools: Unity, Unreal Engine, and programming languages like C# and C++. Data analysis and visualization, extracting insights from data and presenting them visually. Tools: Python, Pandas, Matplotlib, R, Tableau. Cloud computing, delivery of computing services over the Internet. Providers: AWS, Azure, Google Cloud. Importance: cloud computing offers scalable resources and services for applications. Internet of Things, IoT. Network of physical objects embedded with sensors and software to exchange data. Applications: smart homes, industrial automation, health monitoring. Robotics, designing, constructing, and operating robots. Applications: manufacturing, healthcare, space exploration. Career opportunities in computer science: software developer, engineer, designing, coding, testing, and maintaining software applications. Data scientist, analyzing and interpreting complex data to help organizations make decisions. Cybersecurity analyst, protecting an organization's systems and data from cyber threats. Network administrator, managing and maintaining computer networks. AI, ML engineer, developing algorithms and models to enable machines to perform tasks. Web developer, creating and maintaining websites and web applications. Database administrator, managing and maintaining databases, ensuring data integrity and security. Systems analyst, analyzing and designing information systems to solve business problems. Core areas of computer science: algorithms and data structures. Algorithms definition. Algorithms are step-by-step procedures or formulas designed to perform a specific task or solve a problem. They are the backbone of all computational processes. Characteristics of algorithms. Finiteness. An algorithm must always terminate after a finite number of steps. Definiteness. Each step of an algorithm must be precisely defined. Input. An algorithm has 0 or more inputs. Output. An algorithm produces at least one output. Effectiveness. All operations must be sufficiently basic that they can be performed exactly and in a finite amount of time. Examples of algorithms: sorting algorithms. Organize data in a specific order, e.g., quicksort, mergeasort. Search algorithms. Find specific data within a structure, e.g., binary search, depth-first search. Data structures definition. Data structures are specialized formats for organizing and storing data. They enable efficient access and modification of data, which is crucial for optimizing algorithms. Common data structures: arrays, a collection of elements identified by index or key. Linked lists, a sequence of nodes where each node contains data and a reference to the next node. Stacks, a collection of elements that follows the last in first out, LIFO, principle. Queues, a collection of elements that follows the first in first out, FIFO, principle. Trees, a hierarchical structure with a root node and child nodes, used for representing hierarchical data. Graphs, a collection of nodes connected by edges, used to represent networks. Hash tables, a structure that maps keys to values for efficient data retrieval. Importance of algorithms and data structures. Efficiency. They are essential for writing efficient programs that can handle large amounts of data quickly. Optimization. Proper use of algorithms and data structures can significantly optimize the performance of software applications. Problem solving. They provide systematic methods for solving a wide range of computational problems. Scalability. Efficient algorithms and data structures ensure that applications can scale to meet increasing demands. Foundation. They form the foundation of computer science, underlying almost every area of study and application within the field. Detailed concepts and algorithms and data structures. Sorting algorithms. Quicksort uses a divide-and-conquer approach to sort elements. It picks a pivot element and partitions the array around the pivot. Mergesort, also a divide-and-conquer algorithm that divides the array into two halves, sorts them, and then merges the sorted halves. Insertion sort builds the final sorted array one item at a time, with the assumption that the first element is already sorted. Search algorithms. Linear search checks each element of the array sequentially until the desired element is found or the array ends. Binary search, efficient algorithm for sorted arrays. It repeatedly divides the search interval in half and compares the target value with the middle element of the array. Data structures, arrays, simple and easy to use. Fixed size. Fast access to elements using index. Linked lists, dynamic size. Easy to insert and delete elements. Slower access compared to arrays due to traversal. Stacks, supports operations like push, add an element, pop, remove an element, and peek, view the top element. Used in problems like expression evaluation and backtracking. Queues, supports operations like enqueue, add an element, dequeue, remove an element. Used in scenarios like task scheduling and breadth-first search. Trees, binary trees. Each node has at most 2 children. Binary search trees, BST. Left child nodes have values less than the parent node, and right child nodes have values greater than the parent node. Heaps, a special tree-based structure that satisfies the heap property, max heap or min heap. Graphs, represent networks of nodes, vertices, connected by edges. Types include directed and undirected graphs. Common algorithms, depth-first search, DFS, and breadth-first search, BFS. Hash tables, store key value pairs. Provide average O(1) time complexity for insertions, deletions, and lookups. Use a hash function to compute an index into an array of buckets or slots. Applications and importance. Programming efficiency. Choosing the right data structure and algorithm can drastically improve the efficiency of a program. Software development. Most software applications rely on efficient data handling, from databases and web servers to mobile apps and embedded systems. Data analysis. Efficient data structures and algorithms enable the processing of large datasets in data science and machine learning. Competitive programming. Understanding algorithms and data structures is crucial for solving complex problems under time constraints. System design. Designing scalable and robust systems requires a solid understanding of algorithms and data structures. By mastering algorithms and data structures, students and professionals can develop a deep understanding of the core principles of computer science, enabling them to tackle a wide array of challenges and innovate in the field. Thanks for watching. Please don't forget to like, share, and subscribe for more such videos.